Okay, so good evening, everyone, and welcome back to this series, what is titled as All About Neutrinos, the online interactive lecture series for general audience. Uh, Today's talk is a bit historic in the sense that we have reached a few milestones. This is the 30th week of this series, and then also the 60th such lectures. These lectures have been very well received by the both younger and older audience, and this has been also, bringing a lot of attention to the videos that are put up on the YouTube, and bringing up a lot of interest among the younger generation. So please keep doing this, and please bring more and more of your friends onto this series, and celebrate the science that we want to really showcase here. So with those few words, let us start today's lecture. Before I even start going, let me first thank Professor Ishwar Reddy, the making this kind of lecture possible, and thank you as well as Professor Sivarani Thirupathi for agreeing to give this lecture on really short notice. So today's talk is titled, as you can see, is Role of India in Building the 30-meter Telescope to Discover the New Frontiers in Astronomy. For some of those who are probably not familiar, let me tell you, TMT along with the other 7 experiments were termed as mega science experiment of this country. And not long ago, just a year back, we had organized a very successful science campaign involving these 8 experiments, of course, in coordination with the DAE, DST, and NCSM. And on this very same series, you already heard many of the mega science projects. Maybe a few are left, like Maze and ITER and so on. Probably they will also feature soon. But yes, today we are going to have a talk on TMT. And TMT has been all along the year-long campaign is one of the most attractive. It attracted a lot of attention of younger audience to its stalls and its models and so on and so forth, which also reflect the instrumentation and the outreach and various aspects of this project, some of which I'm sure you're going to hear today. So let me also take a minute to introduce today's speaker, Professor Sivarani Thirupathi. She is a professor at the Indian Institute of Astrophysics, Bengaluru. Before joining IIA way back in 2009, she was postdoc at CNRS postdoc in France, and INAF postdoc at Observatory Trieste, and JINA Research Associate at Michigan, and also SDSS postdoc at the University of Florida. She was awarded as an architect of SDSS 3 Marvels project for her significant contribution to the pipeline. She is currently a member of TMT Science Advisory Committee, as well as co-chair from India, and also leads the science instrumentation development in India for the TMT project. She was working lead for the science group named as Origin of Chemical Elements for the Mauna Kea spectroscopic explorer, and her science interests are early chemical evolution of Milky Way and the local volume. So with these few words, let me hand over the platform to Professor Sivarani Thirupathi for a talk, which is titled as Role of India in Building the TMT 30-meter Telescope to Discover the New Frontiers in Astronomy. Over to you.
Thank you, Satya, for this elaborate, nice introduction and very generous introduction, and also giving a kind of overview of the context of TMT in this mega science projects. And I would like to thank the team, so the TMT India team, for all this wonderful work. So with this, I'll start. So I'm trying to give some glimpse of overview of the telescope itself, what is the capability of the 30-meter telescope, and briefly introduce what is the exciting science it will be doing based on what we understand currently, and then describe some contributions India is making in building this observatory. So this is the, as you would see that this is a mega science facility, big facility, and single country cannot build such a big facility. So these are the partners, and you would see California Institute of Technology, Caltech, and University of California observatories. And Aura is the Association of Universities Research in Astronomy. That is all in US. And then the Garden and Betty Moore Foundation, that is also part of US, and Japan through their National Institute for Natural Sciences, and then China through the NOAC is the National Astronomical Observatory, I think. Yeah, then Canada, and so India is funded by Department of Science and Technology and Department of Energy, and these are the participating institutes, IAEA, IUCA, and ARIES. And TIFR through DAE, TIFR is also part of TMT contributing to this project.
Yeah. Sivarani, can I interrupt? Is it possible to move your screen a little lower? I mean, that's right. Maybe a little possible. Yeah.
Okay.
Perfect. Yeah.
Okay. Okay. So thanks. Yeah. So just to give you a context, how big, so this is the comparison of the current telescopes what we have. What you see here is the 2-meter Hubble telescope, Hubble Space Telescope, and which is a single mirror, 2-meter size. And the 10-meter Keck telescope is shown here. And these are the what is shown in the below are the future telescopes, future large major facilities which are coming up. So there is a GMT is it contains like 7, 8-meter telescopes, and jointly it makes up like 24 meters. And TMT is the 30-meter and made up of several 492 segments to which will make up 30 meters diameter. And this is the European Large Optical Telescope. And so if you look at the dome size, so the telescope is the building which hosts the telescope. So this is what is these are the 8-meter telescopes, which is the Subaru telescope in Hawaii, and Gemini telescope, again, it's in Hawaii. And this is the 30-meter telescope. And this is the GMT, and this is the European Large Telescope. What you can see is and I have also put Taj Mahal in the context. So these are really huge buildings. And if you look at the size of the aperture or the mirror size, the telescope mirror size and the building size, you would see that TMT has the most compact dome. A building is very compact. And you can see here, it's a very unique design. So you can see this, the entire structure moves and you have this opening here. So this is called a Calotte dome structure. It's very unique and it's compact, and also it's very quick. In one of the important aspect of TMT is it can within from any part of the sky to any other part of the sky, and any instrument it can switch within like 5 minutes is the kind of time which is given between switching objects. So it's very agile telescope. And this is the optical layout. I have compared TMT and the European Large Telescope here. So the primary is the 30-meter. You can see my cursor, right, moving. So this is the 30-meter primary. The light comes to the primary mirror and it reflects to the secondary, and then it comes back, and there is a tertiary which directs the lights to various instruments, which are, I would show in the other slides how these instruments are mounted. In the case of ELT, you have several mirrors, and there are about almost 5 mirrors, and compared to ELT, which is only 3 mirrors. So this is another aspect of TMT. The 30-meter size is an optimal size to have and to build instruments without having adaptive optics, that is additional active and adaptive optics to feed the instruments. So it's an it's a optimal size that a fully seeing limited instruments should be possible. That gives a advantage for TMT to have high throughput with fewer mirrors, and it will have large throughput in the blue wavelengths. So these are unique features of TMT. And here I just show there's a ray diagram which shows how this tertiary mirror feeds the light to different instruments which are permanently mounted in the either side of this platform. This is called the Nasmith focus. So there are two platforms. So one platform is dedicated to the adaptive optics instruments, and other platform is dedicated to the seeing limited instruments. So there is a adaptive optics facility which would feed all the instruments in this Nasmith platform. And why large telescopes? So it's kind of obvious to everybody. Like it enables us to see further and fainter because it has a large collecting area. As you have larger collecting area, you can see fainter objects. And another aspect is you can also resolve tiny features, small features. When you all of us are familiar with this Rayleigh criteria. Like, so if you a point object will be seen as a diffraction pattern, like what you see, and objects which are closest you could separate, that is depends on 1.22 lambda by d. That's diffraction by a circular aperture. So you can resolve fainter features and also you can go deeper. And however, atmosphere degrades this because the light comes from the light from star or any object comes through the atmosphere, and the Earth atmosphere is turbulent and it distorts the plane wavefront which is coming into from the star or an object. So to achieve the diffraction limit of the telescope, we have to have what is called an adaptive optics supported facility. So here a schematic diagram is shown. So you have a light is coming and you have a deformable mirror which kind of acts opposite to this aberrations created by the wavefronts. And so basically the light comes here and it's separated into two part. One part goes to our instruments, and other part goes to a wavefront sensor which senses this distorted. So wavefronts are basically, the sensors are something like this, what is shown in the left. So you have a large array of lenslets. So something like this, you would have several lenslets, and in the case of perfectly plain wavefront, you would see the dots, the images are equally spaced. And when the wavefront is distorted, each lenslet would see these point sources and this image will shift. So individual images are shifted, and this is how one would infer the tilt in the wavefront, the distortion in the wavefront. And this is corrected by a deformable mirror. And this loop has to be closed within the coherent time scale, which is typically like something like 7 milliarc seconds or milliseconds or so. So with the closed loop, it has to be corrected. So that's how one would be able to achieve the sharpest image, which is given by this diffraction limit of the telescope. So here this is the image which is uh, after an adaptive optics corrected image, and you could see individual short exposure would show like a speckles, like you would see tiny dots. So these tiny dots are like larger the telescopes, these dots split into smaller and smaller. So you would see many more substructure in a larger telescope. And when a long exposure integrated image will look like this. So instead of getting a very tiny diffraction limited sharpest image, we would get a blurred image, which is due to the seeing of the atmospheric turbulence of the of our Earth atmosphere. So, so what is done is normally one can use bright stars close by or a laser, artificial laser star. So what is done? Either you shine a laser, which would at 10 to 20 kilometers, it would emits due to a fluorescence of this water vapor. You would see an artificial star, or one could shine a sodium laser, which would at 90 kilometers around the mesosphere or so, we would have it will resonantly, these sodium atoms in the atmosphere would absorb these laser light and re-emit and forms an artificial star. So this is a kind of the artificial starlight is created. So, however, so what you can see is this is the wavefront which is coming from the star. But the artificial star created by the laser is at much lower heights. So there is a cone for which we don't sample the turbulence. So this is called the cone effect. So we don't exactly model. If you are using this as a reference star to correct the atmospheric turbulence of Earth, we are missing this cone, the either side of the cone. So this is kind of corrected by using several laser beams. So this is called multi-conjugate adaptive optics system. And so this is like, so different, one also should have deformable mirrors which are conjugate at different heights. So it's like a tomography. You would have the deformable mirrors which are at conjugate at different heights of the atmosphere. So that way one could model the turbulence. So this is the kind of, again, kind of a schematic diagram which shows how a multi-conjugate adaptive optics system works. So either it could be reference stars or laser stars, artificial laser sources, which would form these reference system. And so by using these several reference and laser stars, we could observe a large part of the sky. Otherwise, we are limited to very narrow sky position. If we are just using only one laser source or a reference star, we are limited to the coherence, what is the isoplanetic angle, which is about few arc seconds, about 2 arc seconds for Hawaii, for example. So we are limited to a very narrow sky coverage, but by introducing several artificial stars, we would be able to kind of cover the entire larger portion of the sky. So this is called the multi-conjugate adaptive optic system. It's a kind of a tomography of inferring turbulence at different heights. So this on the rightmost, you can see this, how this the shifts of these wavefront sensing elements are shown here. So in terms of, if you compare the angular resolution of, yeah.
Can I, will you be able to take some questions?
Yeah, sure.
Okay, so there's one quick question from Hariom Sagarwal that says, why the wavefront is distorted? Why we are expecting it because the neutral photon doesn't bend?
So, okay, so when light is coming, like we assume this, it's a plane wavefront because it's coming from a very large distance, but the atmosphere causes turbulence. So atmosphere causes turbulence, in a sense. It would have different densities, temperatures, and so this would act like a different path differences. Each would have different path differences and phase differences, which would kind of delay certain part of the wavefront, and so that's how it causes distortion. Does it answer?
Okay, I hope so. Yeah.
Okay.
Thank you.
Yeah, because the refractive index also changes with the temperature, different layers.
Yeah.
Of the air.
Yeah, so we have, this is called, there is a Freed parameters or an isoplanetic angle. So for a spatial scale of like 2 arc seconds, for example, Hawaii, so that is the kind of typical expectation. It depends on site to site. So that's why one wants to go above the turbulence layer so that we have minimum. So it's mostly high altitude sites one would prefer because these turbulences are minimal. So we are above the inversion layer. So, so that's how you can get more stable atmosphere. Yeah. But so within a patch of like 2 arc seconds, you expect the refractive index to change. So that's the kind of, if you're an object and a reference is within that part of the sky within 2 arc seconds or so, you would expect that you are sampling the similar turbulence part of, yeah. Okay. Okay. Yeah. So I have just a metric to define. So this is what is called a point source sensitivity. So this is defined as like an exposure time needed to reach a given signal to noise. So this is a metric which defines a telescope or any optical system, what is the efficiency of a particular optical or imaging system. So in the case of a seeing limited, so where we don't have an adaptive optics assisted observations, then the sensitivity goes with diameter square. So it's basically area. So this is just coming from the light collecting, the area of light collection. But in the case of adaptive optics assisted observations, the sensitivity goes d power 4. So this is primarily coming from, this is again, it's very specific to the background limited objects. So if you look at the, for TMT would be observing objects which are like 27th magnitudes. But the sky background at infrared wavelengths are 18 to 21st magnitude, depends on where observing close to moon or what is the different sites, like emissivity of a given site. So the background varies between 18 to 21st magnitude, but where TMT can observe objects which are up to 27th magnitude. So basically most of the observations are background limited. So that means background is brighter than your objects. So let's say background is about 100 photons, you are detecting 3 photons above this 100. So 103 photons is what you are trying to see. So in the case of such a background limited observations, when you go for a larger telescope, when it's also adaptive optics assisted, the image is sharper. So it means your background area of the background is also lesser. So that
Yeah, sorry, we have gone off.
okay. I don't know why it's not
Yeah,
going up. Okay. Yeah. So I just wanted to show, like in a case of background limited observations, so the sensitivity of observations goes d power 4. So as you go for larger and larger telescopes, when we are doing a background limited observations, adaptive optics is really essential to take a full advantage of the aperture what we have. And S is called the sterile ratio. So it's kind of 1 for an ideal adaptive optic system. But typically it is like 0.7 to, like sometimes in the blue wavelengths, they are very poor. It's about 0.4. So this is again a diagram showing us simulations. So it's an image which is not adaptive optics assisted, looks blurred, and as you see the best adaptive optics system, like diffraction, you can see this airy disk rings around this. So as you go, when the image gets sharper, you also sample very little part of this background, so that your background is also less. So the noise introduced by the background is less. So yeah, this is again just to show a comparison of other telescope, the competing telescope like the European Large Telescope, which is much bigger than 30 meters. It's 39 meters. So however, what you can see is this is the what is the performance of TMT, and these are the for different adaptive optic system. So at first light, ELT would have an adaptive optic system, which is called Atlas, and then later it will have Mauri, which is the next generation adaptive optic system. But what you can see is even though TMT is smaller than ELT, it still do much better than ELT at up to 1.2 microns. This is again coming from the more advanced adaptive optic system what TMT has compared to ELT, and also fewer number of mirrors. So this is the TMT instrument suite. Like you can see this, the tertiary mirror, which deflects light to various instruments, which are permanently mounted. So any time it can just switch between instruments very quickly. And that's how it's kind of equipped for doing fast transients and any interesting objects. So we should be able to be on sky much quicker than any of the other large telescopes. This is another view of this in TMT instruments. And this is the observatory view. And yeah, so these are the various different instruments. These were the concepts during 2005 to 2006. And this has changed a lot. This is what are the concepts in the currently. So whatever you can see, this is WFAS. It's a wide field optical spectrometer. And this is in 2005, this is how the spectrograph looked. So it's quite different. And so I just switched to the key sciences, what TMT would be exploring. Some of these main area of sciences which TMT would be doing is probing the nature of dark energy, dark matter, and also these fundamental physical constants, whether are they really constants? Do they vary with redshifts, or do they vary with high gravity? So all these can be probed with TMT. And TMT can also probe the very first objects, very first galaxies which are formed in the universe. It can take spectra of first galaxies which are imaged by James Webb telescopes. And TMT is also, due to its spectroscopic capability, it can probe the chemical signature and can say when and how these first objects are formed. And again, the solar system objects can also be studied in very high detail, like we can resolve solar system objects up to a few kilometers, which is very interesting. And TMT can also probe the exoplanets and look for signs of life, like looking at oxygen and other biosignatures. And TMT can also probe some of these very interesting comets and interstellar objects which come into a solar system and take spectra of them. So that is also interesting to know how the Earth got its water and other aspects. So this is again a simulation showing how TMT would study the structure of galaxies and understand how the dark matter distributions at very high redshifts. So basically this simulation shows baryonic and this simulation actually shows the dark matter distribution. But we can take different lines of sights, the spectrum of different lines of sights, and probe what are the substructure, how many intervening galaxies are there at these redshifts. And this would really tell us what is the nature of the dark matter, whether they are cold, warm, and what kind of dark matters would produce these kind of structures at these scales, at different length scales. So this is again showing how quasar absorption lines can be used. So this is light from quasars, and as the light comes through different intervening mediums, you would see the absorption lines due to that. And these absorption lines carry the signature of their temperature, densities, and chemical composition. So it's really wonderful to probe the entire kind of line of sight physical and chemical properties of these intervening galaxies between the quasar and us. And these quasar absorption lines can give various absorption lines, and the high resolution optical spectrograph in TMT can probe very diffused, lowest diffused ISM, IGM, not ISM, intergalactic medium. And these, because at high resolutions, we can resolve many of these atomic lines, and several of them have these multiplets. So we can also probe these atomic multiplets, whether their separation changes with time, that is, changes with redshifts. So this is primarily coming from this hyperfine splitting of these lines. So this fine structure constant, whether it varies with different redshifts and our time. So that can be probed using TMT. And this would kind of needs very stable spectrograph, because you are looking at these tiny changes in these multiplets, the separation between various multiplets at different redshifts. So one would want very stable spectrograph, which over a long wavelength, the optics design has to be very carefully designed, so there is very less distortion in the wavelength scales, and it's stable up to like 20 meters per second over several years. And this is again a simulation of what is HST image of Andromeda, center of Andromeda galaxy, and what is the TMT infrared imager and spectrograph would give. So we can see the resolutions are much superior. And this is again another simulation showing how TMT can probe the centers of our Milky Way. So this is one of the recent Nobel Prize. It's based on the Keck observations of our Milky Way galactic centers. One can see the stars change, their positions change. These are from 1996 to up to 2002. These observations, you can see actually the position of these objects in the center changing, and you can actually probe their orbits, and thereby we can probe the masses of these black holes in the center. There are also a lot of strange objects which are found close to the Milky Way galactic center, close to the black hole. So these are called G objects. We still don't know these nature of these objects, and TMT should be able to take spectra of these objects. So it would be very interesting to study at high gravity, what are the physical processes which goes into. And this is another thing showing this, maybe this would have come in several other talks. So neutron star mergers, we think they make the heaviest elements in the cosmos. So we know supernovae make a lot of heavy elements like iron and various heavy elements. But we also find elements like uranium, thorium. And so these heaviest elements, currently the theory indicates that we can't make such a heaviest elements during supernovae explosion. And so one of the possibility is making these elements during a neutron star merger events. So the unique thing about neutron star mergers is they can make, because it's highly neutron rich, as two neutron stars come together, they kind of decompress, because of the gravity, and the degeneracy of this compact neutron star is lifted, and then from neutrons you start building protons, and so you can start making neutron rich nuclei all along the neutron drip line, and then make all the heaviest elements, and they radioactively decay to uh, fall at this the valley of stability. So this is kind of a very robust process. It can they can make all the highest neutron density, neutron rich nuclei can be made by these neutron star mergers. So this is also supported by the observations by metal poor stars. So what is shown here is there are very old stars in our galaxy, which are about 13 giga years old. And so these are, I am showing some, about 6 of them. They are highly rich in the neutron capture elements, like they have been detection of thorium and uranium in these objects. But if you look at the relative abundances of, this is the atomic number and their relative abundances. So the blue line indicates the relative abundance pattern of these elements in our sun. And these 6 objects show exact similar pattern like our our sun. So it means an object which is highly neutron rich, neutron R process rich, or the neutron capture elements rich, is considered to be due to one episode of one rare event of neutron star mergers, which made these highly rich mm, um, gas ejecta, and a star which is formed from the ejecta would have this pattern, and we see that sun and this single episode, the pattern is very similar. It indicates that sun would have received several generations of such a supernovae or a neutron star merger events, but a single episode and several generation of merging events have produced same pattern. So it means some universal process, which is it's called, we call it as a universality in our process. So there is a universality in the our process. So it indicates there is a robust way of making our process in the universe, which doesn't depend upon the environment, astrophysical environment of this of the sites. So this is again indicating TMT should be able to find very many such old stars or the primordial stars in our galaxy. So you can see this, we currently, the record holder is metal poor stars, which is like 10 million times metal poor than our sun. So it has for every iron atom what you see, or for every 10 million iron atom, you would see one iron atom in this star. So it's really metal poor. Metal poor means they are very old. So we know only few handful of them, and TMT should be able to study several of them in detail. And TMT can also detect uranium and thorium in some of these extremely metal poor stars. That also gives insights to how elements are produced, heaviest elements are produced in the universe. And this can constrain the role of neutron star mergers and supernovae. Currently, we still, neutron star mergers don't completely agree with our predictions, because the evolution time scale of neutron star merger doesn't match with the metal poor stars. We find very old stars still have some neutron capture elements. So that indicates that supernovae, the neutron star mergers have to evolve too quickly, too soon. They have to contribute to the galactic enrichment. So this is another thing indicating, like, you can actually image the birth of planets around stars with TMT. And so this is a coronagraph. Actually, you mask the light from the center of the star and try to image the disk around the star. And This is again, you can also probe the gaps. If there is a protoplanetary disk in which already a planet is formed, it would accrete the gas in the disk, and you can see this kind of gaps. This also can be imaged with TMT. And TMT can also study this transmission spectroscopy. So when a planet crosses the exoplanet, when it crosses the disk of a star, the absorption of this starlight can be observed. And any outer atmosphere, it would also have the absorption light features of this mm, the planet itself. So we could detect all these key important lines like oxygen, water, and in the optical wavelengths, and carbon monoxide, carbon dioxide, and various other elements can also be detected. And as this planet crosses the stellar disk, it is also shifting. It's moving very fast at few kilometers per second. So these would also be seen as Doppler shift. For example, you can see this as a signature like this, a Doppler in the cross correlation of this spectral line. You could see a cross correlation signal. So this is called high resolution Doppler spectroscopy of exoplanets. And TMT, one of the key sciences for TMT is detecting oxygen in like around M-type stars. So this is the direct detection of life on another system, an Earth-like system around external galaxy. So, and TMT can also take, this is directly, so this is a coronagraph where you have masked the central part of the star, and these are the residual light. And what you can notice is there are two circles drawn here. So the green is the actual planet, but this red circle is a speckle. So these are the residual speckle light, which is not coming from the planet, but it is due to the residual starlight. But there is a wavelength dependency. The speckle light would change with wavelength, but whereas the exoplanet position would stay same. So if one combines the imaging along with spectroscopy, one also would be able to suppress these artificial signals which are coming from speckles. And this is again, when you combine both high dispersion and coronagraphy, how we can remove the signals of speckles and retain the signal which is coming from the planet. And this is, I think, yeah, so how the instrument works for, so if somebody needs, I would go through that. Yeah. So another important aspect of TMT is it can study isotopic abundances of comets and other solar system objects, which are very essential to understand the origin of our solar system. So I moved to the role of India-TMT in building this observatory. So this shows various subsystems which India is making. One is the primary mirrors. We polish about 86 segments of this primary mirrors. And each segments is also supported by a support assembly, because this 496 segments should form a monolithic 30-meter diameter mirror. So these actuators and edge sensors kind of try to warp and support and make a monolithic M1 30-meter mirror. And we also contribute to the coating of this mirrors. And then observatory control software, how the entire software, there are so many subsystems and servicing systems which are there in the observatory. And it also has to talk to the instruments. So the entire control software is made in India. And we also contribute a lot to the instrument development. So this is the different, so what you see is this is, I think, so we have this in the different segments color coded, showing what different countries' contributions. So you can see India is making about 86 segments. And so these segments are 1.44 meters, and they are very thin, like only 45 thickness. So this is made in a facility close to Bangalore. It's about 30 kilometers from Bangalore. And so the way it's called a stress mirror polishing. So to have a hyperbolic 30-meter mirror, each segment would have a different shape. So in order to achieve this different shape, what is done is called the stress mirror polishing. So we have the polishing tool is a normal spherical polishing tool, but you kind of warp this stress by introducing some stress. So these are these bonding pads and levers where you can you can stress them appropriately so that and then you use the normal spherical polish, and once you release this mirror, then it would achieve the required shape. So this is called a stress mirror polishing technique. So all these mirror blanks have arrived from Japan. So they have been inspected. So this is kind of a slightly older slide. So things have gone much ahead, and the facility is ready to receive some of these machineries to start polishing. And there are various profilometers which would measure the shape and the polishing of these segments. So this is the segment support assembly. And so this is the 30-meter mirror, and each segment is shown here. And so this entire different segments should act as one monolithic mirror. So this is supported by this segment support assembly, which can tip and tilt and also warp to make a shape of a monolithic 30-meter segment. So it also can warp for the temperature changes during the observations. So and also changes due to gravity. So it can support all this, and it also can accommodate some of the errors induced during polishing. So the segment support assembly can warp to accommodate some of these errors due to. So the major challenge here is the segment supposed to, the stroke, what is the movement of this segment is about 2.5 but it has to, the actual requirements of these, so the support shouldn't introduce errors beyond 11 nanometers. So to have such a large dynamic range is something which is really challenging here. And this kind of shows various things under these segment support assemblies. So you can see a lot of wires hanging on. So it's a very complex system. And these are some of the so there are various systems which are so which is part of this SSA, and which are the edge sensors and other things which would also sense, and the SSA would kind of move to appropriate locations. So these are various different parts which are made by the industry within the country. And so these are some of the team which they have gone to Pasadena to test these and successfully done this assembly of one of these SSAs. And this is the team in India, which is developing this telescope control system. And so they have completed this preliminary design review. So these are some of the pictures of that. And this is the observatory control of software architecture. So this is a kind of a backbone for the entire observatory. And so this is entirely being done in India by the ThoughtWorks software company, and the astronomers and the team of India-TMT would are coordinating with them. And these are the first light instruments. It's called IRIS, in infrared imaging and spectrograph. So one of the main science goals of these is resolved spectroscopy of galaxies at 2 to 6 redshifts. They can actually detect the Lyman alpha emission from the highest redshifts, like up to redshift of 12. And these have an ideal synergy with the James Webb telescope, space telescope. And so compared to James Webb telescope, which is having a resolution of 0.1 arc seconds and has a spectral resolution of 2700, you could see TMT IRIS has about 4 milli-arc seconds. It's the spatial resolution of TMT is really very, very quite high compared to even the space telescopes. So some of the India's contribution is I was talking about this guide stars to sense the wavefronts. So this catalog is being developed in India, and India is also contributing to the data pipeline of this instrument. And this is a simulation of the same instrument. And so IRIS can kind of resolve like 36 kilometers of these Jovian moons, and up to less than 0.1 kiloparsec of at redshifts of 5. So it's really very unique instrument. And another first light instrument which India is contributing a lot, we are contributing about 20% of the development of this instrument. So it's called the wide field optical spectrograph. Some of the key sciences is the tomography of intergalactic medium, and deriving the chemical abundances of intergalactic medium between quasars and other galaxies. So it is also have large capability of doing local volume of galaxy archaeology. And so this is another instrument which is being led by India. So all the 3 other first light instruments are led by mainly the institutions in California. So this is first instrument which is outside California and outside US. So India is leading this development of this high resolution optical spectrograph. And some of the key sciences are this process elements origin and cosmological lithium problem. So we currently know that the Big Bang, whatever is seen from CMB predictions of the lithium abundances and what is seen in the old metal poor stars do not match. There is a difference of 3 to 5 times lower values which is detected in metal poor stars. So we don't understand the discrepancy. So with TMT, we can observe this possibly the first dwarf galaxies which are formed in the universe, and we could derive lithium abundances in these very old stars. So this would be the first time it's possible to do with the arrival of TMTs. And these are other aspects of this high resolution spectrograph. We can do like exoplanet derived masses of them, and we can study the variation of fundamental constants and the chemodynamical history of the entire local volume of galaxies. So these are some pictures of that we want to talk. This is during the TMT Science Forum in Xiamen in China. So just 2019, about a year ago, a little bit more than that. So, and so this is the science development team, and what is India's participation. So you can see this is 20% of India's participation in the science team. And these are the distribution of India's science team across different science areas. And dominantly, you can see Milky Way and stars is the majority. So that also falls in line with that India is leading one of these high resolution optical spectrograph. So this membership for this international science development team normally comes every January every year, and there is also possibility for, so anybody with a PhD degree can become a member, can apply for a membership, and the students who are doing PhD can still apply as a junior members with endorsement from their supervisors. And these are some of the pictures of this science forum which happened in Infosys campus in Mysore. And TMT is also, India-TMT also conducts a lot of workshops to train students to understand these complex instruments with various multi-objects, spectrographs, how to do science with such complex instruments using archive data from similar instruments on 8 to 10 meter class telescopes. And these are again some pictures from the workshops at Aries. Yeah, thank you. Thanks for listening. I would be happy to answer.
Thank you very much, Professor Sivarani, for this wonderful talk, which really took us from all the way from very exciting, unexplored physics, all the way to the big challenges of building very, very complex instruments. And what is also, of course, very, very heartening is to know India on an average, giving more than 25% or 20-25% of contributions, not only for physics but also building all these complex machines, the control software and various other interesting instruments. Which is also what is, I think, heartening to know is that you are involving the Indian industries in a big way and bringing them an upper edge over the rest of the world in building, let us say, basic science instruments. And last but not least, some of the opportunities that you briefly touched upon to both the PhD students and also, postdocs and so on, to work with this exciting physics, I think is something which to really grab. So thank you very much for your talk covering the entire range of the very prestigious and, as I said, one of the mega science project of TMT. There are several questions both on YouTube as well as Zoom. I would like to take them one by one. Okay, I see one question right away is from Professor Vivek Datar. You can go ahead and ask.
Okay, can you hear me?
Yeah, sure.
Yeah. Okay. There are two questions. One is is Hawaii again on the? Will it happen in Hawaii or is it? There is still problems because I heard that things are going in the right direction for Hawaii.
Yeah, currently with NSF has a lot of interest in exploring Hawaii again. So there is efforts going on in that side. But we still keep the backup site La Palma. Yes.
The other question relates to the change of fundamental constants with time. Now, the way you infer the time, go back in time, is through the redshift.
Yes.
Okay. But then that is also used, the way the line shift is also used to infer that Z, isn't it? Or you use some other complementary information?
Yeah, these are, yes, it's not the overall.
It should not be a bootstrap kind of thing, right?
Yeah, so it is not exactly shifts, it's between these multiplets. So you have this hyperfine splitting of these atomic lines, which has known separations. I don't know whether So these are these triplets of, so you can, basically the study is focused on separation of these multiplets. So overall shift is what gives you a red shift, the entire.
But wouldn't the separation also scale with Z? Because the energy is, let's say there were a photon, that would have shifted.
Yeah, so the overall shift is like several kilometers, like about 2,000, 3,000 kilometers. It would, like, basically you would see this rest wavelength 1,000. So actually we would be seeing them in at actual optical wavelengths. So overall shift is several orders magnitude larger than this tiny shifts between the. But yeah, you are right. Like I don't know. I have not really worked on actual analysis of these data. So how this, when we are looking at few 1 part in million separation, and so basically it translates about like 20 meter per second in terms of
No, no, my
wavelengths.
question is a little more, maybe it's just kind of elementary, that if some energy, the photon energy shifts with Z, then the difference also should shift with Z.
Yes.
So unless you are using some other information to,
No
get at this.
difference. Why do it's a Doppler shift?
Why to change
Difference shouldn't shift.
Yeah. Difference should not switch.
Yeah, actual shift should be, yeah, it's a Doppler shift which is giving the red shift, which is
The
overall
physical-
the pattern should remains the same. The entire the fingerprint of patterns of these atomic lines should remain the same. It's only just shifts.
Okay,
But between the wavelengths, the shift is what is caused by this fundamental constant, the
okay,
fine
maybe.
structure.
Yeah. Thanks. Maybe I'm not.
So, yeah.
Sorry, I kind of took it in wrong direction. Like, okay, thanks.
No problem. We have a question from Purvaja.
Hello, ma'am. Good evening.
Yeah.
I have a question related to stale ratio. So I would like to know, what does this ratio tell us about an ideal AO system, and what is this ratio really means?
Yeah, so if it's a Stral ratio about 1 means it's a perfect, it's a theoretical, like you were seeing a point source by an imaging system. So you would see a diffraction pattern of a circular aperture. So for compared to an ideal system versus the actual performance. So if it's sterile is 1 means it's a perfect system. It doesn't have the energy is within this 1.22 lambda, like like you would see 80% of them, because the rest goes to the wing. So that is the perfect 1 means 1. As the ratios becomes lower and lower, like 0.4 in the typically we see in visual band, so that is poor. So it's 1 is best and lower is poor. So it's compared with an ideal system to the actual system. So ideal is a theoretical. We never have 100% Australian for any imaging system.
Okay, thank you.
Yeah.
We have a question from Professor Govinda Majumdar.
Yeah. Okay. Thanks for this beautiful talk, and I learned a lot from this different topic. I never went through all these details earlier. Now, I have some basic question. If you go back to page 16, I think, where you showed the spectrum, but wavelength range, particularly I want to, this instrument, what are the wavelength range you will study?
16th, I forgot to, I don't know whether I have written any.
No, go back a little bit, I think.
Back, is it?
Back. Where you compare this sensitivity in this.
Okay, this one.
No, okay, yeah. No, I'm just saying that you showed here 0.8 to 2.4, but I think later on you showed the energy wavelength spectrum in the different other wavelength also.
Yeah.
So I just want to know that what is the whole range of your wavelength spectrum in TMT?
Yeah, so it goes from 0.3 microns to up to 25 microns. It's really a wide range. So here I have only limited to the adaptive optics, the first light adaptive optics facility, which starts from 0.8 microns to 2.4 microns.
No, so this 0.3 to 0.8, you will not able to correct through? of the
Okay.
current attractive optics?
So below 0.8, the sterile becomes very poor. So also, okay, so there is a next generation, what we call is the ground layer adaptive optics could feed some of these blue wavelengths. It's possible. But yeah, the performance is better beyond 0.8. But beyond 2.5, we could, it's much simpler. So yeah.
Okay. Okay, thanks. Another small question, I think 1 or 2 slides later, you have shown that many instrument you can replace. I think one back.
Yeah.
No, not that.
This one?
Basically, the point you said that
This
in
one?
yeah, here is this many different instrument. So all of them will not operate together. One by depending on this physics, you will operate this one by one different instrument. So how many total instruments are there like this?
So first light, we have 3 instruments. So this is the wide field optical spectrograph. And here you have this infrared imaging and spectrograph. And then there is on top, there is a high resolution infrared spectrograph. So these are the 3 which will be first light. Then the one which is India is leading is the high resolution optical spectrograph, which comes here. Okay. And then there is a infrared multi-object spectrograph here. And there are few other there is a planetary imager and spectrograph which comes somewhere here. So all these instruments are permanently mounted, and the feeding the light is done by this M3 mirror, which is the tertiary mirror, which deflects to feed any of these instruments. So normally it's proposal based. Different people propose observations, and a given night maybe about let's say 10 to 20 proposals would be executed. So there will be different instrument. Each proposer would ask for different instruments. So you would observe one at a time and switch. You want to reduce the time between switching these instruments. So that is why this kind of an arrangement, which is quite useful in TMT.
Okay, thanks.
Very interesting way of switching, like an accelerator, fixed target experiments. We have one more question on the Zoom, but let me hold Hariom for a while and take a question that was actually asked well before. This is about adaptive optics that you explained quite well, but there is a question. Maybe you can spend a minute just to recap using your slide if possible.
Okay.
Yeah. The question from Ankita. Yeah, this.
Okay. Yeah, so maybe I would start with a simple one. Okay, so for example, this is the picture where you are observing a star, and the atmosphere normally, without any atmosphere, if we have a space telescope, we won't have any turbulence. The turbulence is again created by this change in refractive index, which is caused by temperature variation, density variation. So that's how this, so it's blur the image. So in order to control the blur, so normally this change in this turbulence has a time scale. It is of the order of like few millisecond. So if we can have a deformable mirror which compensates for this, so the deformable mirror is like, you can assume like a rubber, like which can have a very strange shapes, which can be achieved by actuators. So you can have some electronics or electromagnetic things which could, actuators which can push and pull and shape these kind of this deformable mirror so that it can act opposite to the turbulence and try to give you a flat parallel plane wavefront. So this closed loop, so first is there is a sensing. You want to sense what is the tilt or the distortion created by the wavefront. That is done by this array of lenslets. So lenslets are basically the, so I lenslet. I think, I don't know whether I went to here a little bit. Yeah. So basically this, instead of, so there are small lenses, which is receive the light coming from a star, which is imaged by multiple lenses. So each lens will give one image. So you have array of images created by one star, for example. And when there is a wavefront which is tilting or which is distorted, these images would move. So this shift in these images are used to deform this deformable mirror. So that's how one can correct this deformable mirror and then try to achieve a. So this closed loop the loop has to close within few milliseconds.
Okay. There are a couple of more questions on Zoom, but I would like to go to YouTube to take up a few of them. One of the question from Abhinav Chaudhary, it says, this is about edge sensors that you talked about.
Yeah.
He says, what is the application of edge sensors in TMT? Maybe if you can just kind of.
Yeah, so edge sensors are located between the two segments, for example, like, yeah, maybe I can, okay. Yeah, so these are capacitive sensors. So one of these block is fixed onto one of the segments. So between these two segments, for example, this is how an edge sensors are located. So one block is this side, the other block is in the next segment. So the variation in the capacitance. So these are coated by gold. So you have two blocks. So if there is a small shift between these two blocks, the capacitance vary and you can sense them. So then you can move this mirrors and tip and tilt so that it forms a uniform shape.
Very nice. Yeah. Another question is, this is about your calibration. I mean, using the artificial stars. What is the speciality about sodium vapor laser?
Okay, so because Earth has around 90 kilometers above the Earth atmosphere, we have this sodium layer. So by shining a laser at this wavelength can resonantly excite these sodium atoms. So you can form artificial star at very largest height, like 90 kilometers means you are really sampling a large amount of turbulence. But if we are using some other fluorescence or other methods like Rayleigh lasers, then they only go to about 20 kilometers or so. So that way sodium offers a better possibility.
Well, again, come back to YouTube. A couple of questions more are left, but let me take one more. This is Govinda, not Govinda. I have two questions. One is regarding laser stars for adaptive optics. Okay, can we have Govinda?
Yeah. See, my question is on the almost 50% of that is answered by the previous questions about the use of laser beam for adaptive optics. So you said the sodium layer is there about 90 kilometers above the Earth, and that will act like a source, and then the light will come from there to the telescope. When it comes down there, it will go through the atmosphere and it will distortion will take place. Is it not important to know at what height this source is there? And whether if it's not important, then it's okay. Otherwise, you will not be knowing exactly at what height it will come, isn't it?
Yeah, we exactly needn't know the heights as far as, so yeah, so you have touched upon an important thing, but it's a little technical. So so there is some difference between like for example, star comes much above, but lasers are only at 90 kilometers. So there is some difference between the optical path, but this is typically this layer is about 10 kilometers, I think, this height of this sodium layer, but that really doesn't matter much for us. But there is some difference between the actual star and this, so that adds some additional tilt. So normally we have like something called faint sources reference stars we use to correct what is called it's not an it's not a main thing which drives the deformable mirror, but it adds to the correction in the tilt. So it's yeah.
Okay.
But actually, it doesn't matter whether exact height is not an issue.
So a few
But
kilometers range.
yeah, but flux is important. So we need to have enough flux. So
Yeah.
sometimes if there is changes in the sodium layer, that could be.
Yeah. Okay.
Yeah.
Okay. Then I have a second question. You said the black hole, the mass is determined by looking at its orbital moment, and that is observed over a period of few years, like you said 1900 and 19 some.
Yeah, right. Yes.
So is that sufficient to know the position of that black hole? Yeah, here is. Is it sufficient to know the position of black holes over just a few years, or let's say 10 to 15 years? Because it's suppose its orbital period is, let's say, a few thousands of years, for example. Then will it give you any feel of that? With that, will it be possible to find out the mass? That's my question.
So these are stars which are moving around the black hole. So you could see that one can, based on this, one could completely you could cover the entire orbit. So within this years. So
Yeah.
each individual points are given, like you could see.
Yeah, my question is, suppose that orbit takes, let us say, 1,000 years, but your observation is only for, let's say, maybe 1 decade or 2.
Yeah, then it may not be I don't know what is the typical. Yeah, for a black hole in the supermassive black holes, and objects which are few light years away, so you would expect them to move very fast.
Yeah. Okay.
Yeah.
So that is sufficient. Will it give sufficient accuracy in terms of determination?
Yeah. Few tens of years that should be much easier to.
Okay. Okay. Thank you.
Okay. Let me. We'll let Hariom still wait. Let us go to the YouTube. There's one question, slightly general, but how does Ladakh compare with other prime telescope locations in the world?
Yeah, so in Ladakh is one thing, it's very good because of the high altitude. We have low absorption, so our performance in the blue wavelengths are extremely good. Again, because of the cold weather, the emissivity in thermal emissivity in the thermal infrared region, like below above 5 microns to 20 microns, we would have excellent performance. One of the main issue is Ladakh is the seeing, atmospheric seeing is not as good as, for example, Hawaii. It's better than many other sites, but it's not as good as Hawaii. So it's primarily due to the jet streams in the local Himalayan regions. So there are heavy winds, so that the local turbulences kind of creates the poor seeing. So adaptive optics performance is, so basically the coherent time scales would be much shorter compared to Hawaii. So you having an adaptive optic system would be much more challenging, but it's not impossible. But yeah, it's more challenging than, for example, Hawaii.
Okay. Let us take Hariom. Hariom, you have a question. Yeah, go ahead.
Yeah, actually, ma'am, you have shown that there are lenslets to correct the atmospheric disturbances, and you have also told that the order of this atmospheric these disturbances 1 millisecond. Is this correct? Uh, because because I am asking this, why you are considering this at this order is of disturbance is 1 millisecond. This atmospheric, there are temperature or density differences in the atmospheric gas like nitrogen and oxygen. So I'm thinking this is like this is very small. The time should be in like I don't know, microsecond or less than that. You are saying it is in millisecond because this is totally random. Which photon will be like attenuated or scattered somewhere else? So can you like, or is there some problem in my understanding?
Yeah, I don't know. Yeah, I will try to explain. Yeah, so basically it's compared to the wavelength and okay, it's basically you could assume okay like okay, atmosphere, certain length scales, the atmosphere is same. The turbulence scales are same. Like for example, few like here, for example, 2.55 arc seconds is the spatial scale in which the again it depends on wavelength. Like it's for a larger wavelengths you would have the isoplanetic patch is larger and the coherence time scale is also longer. So it depends a lot on wavelength. So for 1 micron, for example, that's the what this values are given. 7.3 milliseconds is for 1 coherence time for 1 micron. So this is the time at which the refractive index would change, or the compared to the entire. So it's not just the entire heights that travel. So you were talking about the scattering. You were talking about much more microscopic, is it? I don't. Yeah, I didn't quite understand.
Actually, I know this is wavelength dependent, but I am saying this this is photon is like suppose hundreds of photons are coming, and out of them some of them will be attenuated according to this attenuation coefficient of the atmosphere at some density and some this temperature, etc. So my question is, this is totally random process, like which photon will be detected, where this whole wave front will shift. So this is, and it is very fast. So
yeah, so you are talking about this photon noise basically, right?
Yeah.
So that is that is much yeah. So if you detect like 100 photons, square root of 100 is the noise. You wouldn't know the uncertainty in the detection, right? What would be? Is it how much would be absorbed and what you would detect? Is that what is that is much
actually,
more random
I
at
was that wave front, the shape of wave front will be random and it will be very fast. Unless suppose there is some cloud or something fixed, then we can say that that much density is here, and that will be like that is like static. But if there is atmospheric this gas turbulence, then it is very fast.
Yeah, the absorption and emission is much more at a faster scale, but actual wavefront distortion is typically few micros, yeah, a few milliseconds. So, but whatever the photon process, what you are talking about is, yeah, it's much faster. That's I don't know whether I'm understanding it correctly. Maybe you can email me, or I don't know whether you can.
Okay.
Sorry.
Okay. Yeah, I know. Actually, there are a couple more questions, but you have answered in some way. One is on the calibration source, which anyway, I mean, just now also you asked about, talked about the sodium vapor laser and so on. The other question was regarding the size of why is the size of the TMT is important. But this, I think the question is, what you said is in terms of the overall size of the instrument versus the telescope, this is much better optimized than its competitors, right? Is that is what you also mentioned? So,
yeah.
Okay.
So otherwise, the instrument size scales with the telescope size.
Right.
So if unlike if you go beyond 30 meters, then we have to make this we need to have an adaptive optic system which tries to make the field of view and this things the images sharper, so that the instruments are in a affordable or comfortable size, where we don't know, like we can't build for example, the largest lenses of calcium fluoride is available at like 500 is the largest size we have. So we have to build instruments within, and gratings cannot go very large. So yeah, the instrument scales with the telescope size. So for seeing limited, so you need to have some adaptive optics to, if you go for very, very large telescopes.
Okay, so with that, I think you have answered a very single question right now on the call. So I would like to thank you on behalf of all the participants, and also, of course, the INO project, which is actually organizing this particular series. And of course, we also wish you and all your collaborators on this great project, and for the exciting physics that is going to come up soon. And more importantly, the fun of the exciting fun, I would say, of building such a state-of-the-art instruments, etc., should actually bring a great joy when you start seeing the physics that you are looking at. And also, I hope many of the younger PhD students and postdocs, etc., will take this opportunity to join your group and also, try their hands in this great project of this country. Thank you very much, Professor Sivarani Thirupathi. Also, thank you very much, Professor Ishwar Reddy, for making this talk happen. Thank you very much once again.
Yeah, thank you, Satya. Thank you so much.